Hello there, ATS 114 students. Dr. John Schrage here, and I am here to talk you through a little bit about Labs 12 and 13, in which we get to apply a lot of the things that we learned this semester to the fields of tornadoes and thunderstorms and hurricanes. Now, by and large, most of the activities are pretty straightforward because you've done most of this kind of stuff already once before at different points in the lab. I do want to steer you towards the right answer on a couple of the questions. For example, you have a question where you have a map of the annual distribution of thunderstorms. It looks something like this colored one. It's not exactly the same, but it has the same sort of idea that there's a big spike in the number of thunderstorm days over the Florida peninsula. And the question is, why would that be? Just to steer you towards the right answer, I'm going to remind you that there were 4 ways to produce vertical motion in the atmosphere. We learned this back in the lectures, and they were to have low-level convergence, or to have rising motion just due to convection as an air parcel was warmer than the air around it, or to have rising motion over a mountain range, we call that orographic lifting, or to have rising motion along a front, which we call frontal wedging. Now, one of those is a good explanation as to why there would be so many thunderstorms over Florida. And I'll give you even a better hint. It has something to do with the sea breeze. Now, in case your section of the intro lecture didn't talk about sea breezes, a sea breeze is a breeze at the surface that blows from the ocean towards the land during the day. And breezes that go from the ocean towards the land during the day are a big part of the explanation as to why there's so many thunderstorms at the surface in Florida. Okay, another point, a number of the questions are in this first part of the lab activity here are about the concept of entrainment. Now, just to remind ourselves about entrainment, I mean, if we have a warm and moist rising air parcel, by definition, it's going to be surrounded by air that is colder and drier than the air in the air parcel. I mean, that's kind of why the air parcel is rising in the first place, right? It's buoyant compared to the air around it. So the air is rising in the thunderstorm because it is warmer and moister than the air around it. But, you know, this whole idea of an air parcel is kind of a fiction. I mean, it's an approximation to what the atmosphere is really doing. But these air parcels aren't somehow like bubbles that can't mix with the air around them because they've got a layer of soap around the outside of them or something. They just mix. Warmer, moist air from inside the air parcel mixes with the colder, drier air from around the air parcel all the time in a process that we call entrainment. It's kind of a mixing process. Well, that process can only make that warm and moist updraft less warm because you're mixing colder air into it, and less moist because you're mixing drier air into it. Both of those processes are going to result in the warm, moist updraft becoming less warm and less moist, which means less buoyant. This is part of the story why updrafts don't just keep going and going and going. As they have experience entrainment, gradually colder and drier air keeps getting mixed in and mixed in. With time, the updraft of the thunderstorm will get colder and drier, eventually maybe even making it so much drier that it isn't even saturated anymore, and you start getting evaporation of raindrops, which is a cooling process. All this has the ability to weaken the updraft and eventually even reverse the updraft into a downdraft. So that's kind of a key to answering certain questions, especially in that Lab 12. I also want to help you interpret this diagram that is in, you have a series of these diagrams actually in Lab 12, where they are showing the data that comes from a launch of a weather balloon that is carrying that package of instruments that we called a radiosonde, that was measuring things like the pressures and the temperatures and the winds at various heights. This particular diagram is showing you as the balloon rose from that station, I think it's Little Rock, what was it seeing in terms of what was it observing with regard to the temperature and the moisture. Now, I don't particularly like the way they formatted the diagram on that particular, figure 12.9 and the figures around it. That solid gray, not the black, but the solid gray line is the temperatures as the balloon was rising. So you can see as it was rising, there's little wiggles as they encountered layers that were warmer and colder and so on. But overall, as it was rising through the depth of the troposphere, the temperature was decreasing with respect to height, as you would expect. And that little dashed dotted line that's gray, that's always off to the left of the temperature curve, that curve is the dew point. So at any given height, you could read down to the x-axis and find out what the dew point of the air was at that height, again, just as measured. And what you're getting from this chart, well, for the purposes of this activity, is noticing that there are layers in which the temperature and the dew point curves are close together, and there's other layers where the temperature and the dew point curves are far apart. If the temperature is quite close to the dew point, this air is almost saturated, maybe even, well, yeah, close to saturated anyway. Very high relative humidity. If the temperature and the dew point are far apart, the relative humidity is very low. So just by looking at this graph, finding places where the temperature and the dew point are close together and places where the temperature and the dew point are far apart on the graph tells you what layers are very moist and close to saturation and what layers are very dry and very far from being saturated. I think there's a question too in this lab that asks you to identify what it called the upper air inversion. Remember, an inversion is a little layer of the air, the atmosphere, where temperatures are actually increasing with respect to height. We didn't use this word upper air inversion, I don't think, in the text and in the lecture. I think we called it a capping inversion, but that's the term they're looking for. So you want to find these little layers where temperature is increasing with respect to height, and that's going to be your capping inversion that the lab manual will be talking about there. There's one other little detail on these diagrams that can be useful. See that kind of dark black straight line that's on there? That is the trace of a temperature profile of an air parcel. If we took an air parcel from down by the surface where the temperature and the moisture was whatever was observed, and as we lifted it according to the dry adiabatic and moist adiabatic lapse rates. This is useful because any place where that curve is to the right of your observed temperature profile of the environment, that gray curve, that will be a layer of the atmosphere where an air parcel that was lifted here is warmer than the air around it. Air parcels will be from the surface will be positively buoyant if you can get them up into that layer. So this is showing us at whatever height above the surface, that this temperature parcel curve is to the right of the environment curve. That is a layer where if we could get air parcels to rise that layer, they would now be warmer than the air around them, and they would rise on their own because they would be positively buoyant. The second half of the activity today is about hurricanes. Now, most of the questions, again, are pretty straightforward applications of things that we learned in other lab activities, but I want to kind of review the structure of a hurricane because a couple of the questions, that's going to be really helpful. So I have from your lab manual, I have a little cross-section of a hurricane down there in the bottom right, and I also have just a space station, I think, a picture of a hurricane as it approaches the United States. Now, I think most of the students are pretty clear at this point in the lecture about the eye of a hurricane, where the eye is that area of sinking motion through the depth of the troposphere, at the area where there was the lowest pressure at the surface and so on. And because of the sinking motion, the skies in an eye are generally clear. They are, the sinking motion means the air parcel is warming as it lowers, and that means it's getting farther from the dew point. That means its relative humidity is going down. And so that sinking motion in the eye, I think most students can picture. Now, in a ring around the eye, we have the eye wall. Remember, the eye wall is that ring of thunderstorms with tilted updrafts. The eye is narrower in the bottom, and it gets wider as it goes up. That was the stadium effect, if you remember that term from your lectures in the textbook. So this is your kind of ring of rising motion. It's the part of the hurricane that has the strongest winds at the surface. Now, around the eye wall, there were these sort of bands, these rain bands, that are also strong thunderstorms that kind of make a spiral shape into the hurricane. I don't want you to get the idea that the whole thing is like pinwheeling or something like that. That isn't generally what the structure of a hurricane is like, but it does have these sort of arms or whatever of these bands of these rain around the outside. And of course, because they are thunderstorms and so on, they have rising motion, and depending on where you are in the hurricane, these can be farther or closer to the eye. But what I want you to notice is that the large-scale environment around the hurricane, don't look at the clouds itself, just look at the large-scale environment around it, hundreds of kilometers around it, is all dominated by sinking motion associated with the hurricane. And that's why it's so clear in the environment around the hurricane. Notice how all those arrows we have drawn up there with that satellite picture, they're all showing areas where it's pretty much clear. The large-scale environment around a hurricane ends up having large-scale sinking motion. That is very much part of the story of how a hurricane works. Kind of an unglamorous part of the story of how a hurricane works, but part of the story, because that large-scale sinking motion results in very dry air. Anytime you have air sinking, it's drying. We're not changing the dew point, but we are increasing the temperature. That increases the difference between the temperature and the dew point, or lowers the relative humidity. So by the time that air gets near the surface, it's really dry. There can be lots of evaporation then off the ocean into that relatively dry air around the periphery of the storm. evaporation of water off of the ocean and into the atmosphere is a big part of the source of energy for a hurricane. So you need to have that very dry air around the outside of the hurricane, that as it gets drawn at the surface back into the hurricane, there can be just lots of evaporation. And think of how wonderful a hurricane is for producing evaporation at the surface. They only happen over the very warmest water. Remember, the warmer the water is, the faster it evaporates. These make these strong winds that produce very fast evaporation. As you blow strong winds across the water, you get stronger evaporation. And the air that you're blowing across the surface of the ocean is relatively dry due to the large-scale sinking motion. All of these things result in just enormous amounts of evaporation at the surface of the ocean. As you remember from the lecture, you have to have that very large amount of evaporation off the surface of the ocean in order to create a monster storm like a hurricane. Okay, there's just one more point I want to make. The lab manual kind of glibly throws out a term that we didn't actually talk about, at least in my sections of the lecture this semester, and I don't think we did in the lab manual, and so let's at least kind of just make sure we're clear about this term. I happen to have a map there. These are winds at jet stream height, and you can kind of see the isobars, and you can, I don't know if you can actually see the little arrows on there, but the winds are basically parallel to these contours that are on here. All semester long we've been doing that. We've been, looking at some set of contours, and we say the wind is going to blow parallel to those contours. Okay, and we kept throwing around this word geostrophic. Both in the lecture and in the lab, we keep using this word geostrophic. We say that winds are geostrophic when they're following the contours. Strictly speaking, that's not exactly right. Strictly speaking, the winds are only called geostrophic if the isobars or the height contours or these lines that are on the map are straight. That's not the normal situation, though. Most of the time the flow is curving in various ways as it goes around troughs and ridges or around cyclones or anticyclones. If the flow is around curved features, if the isobars or the height contours or whatever on your plot are curved and the wind is following these curved contours, the right word for that is gradient wind. And your book, actually your textbook, has like a whole section on gradient wind, but we tend to skip that. It's more detailed than we really need to accomplish the goals of ATS 113. But today in the lab activity, a couple times it just glibly drops this term gradient wind. Don't get bogged down on it. That just means winds that are parallel to the isobars, even if the isobars aren't straight. So like it provides you, I think this is supposed to be with regard to Hurricane Sandy, you can see how there's a cyclone and an anticyclone in the area. It's going to ask you about like the winds around these features, if the winds are gradient. All that means is it's just blowing parallel to these isobars. It's just that the curves of the isobars are curved instead of straight. Okay. Your textbook makes a federal case out of that. It's actually kind of a fairly small point unless you're like a grad student in meteorology. Okay, that's in fact all we need for this lab activity. Your TAs have been well prepared for this, and we'll be glad to help you work through the selected questions from labs 12 and 13. All right, best of luck, and I look forward to seeing you next week.